Hi, my name is Jonas Schouterden. I'm a PhD researcher at KU Leuven. The title of our paper is called Unifying Knowledge Base Completion with PU Learning to Mitigate the Observation Bias. I know this is quite a mouthful, so I'll first describe the task of knowledge base completion and point out how it can suffer from something we call an observation bias. And then I'll describe how we can mitigate this bias using PU learning. So let's start at the very beginning. What is a knowledge base, also called a knowledge graph? It's a set of facts about a problem domain in the world in the form of graph-structured data, that is, entities and the relationships between them. So take, for example, the problem domain of having to match job seekers to job vacancies. Assume that we have a job seeker, Jenny, who has 5 years of experience and knows both the C++ and Java programming languages. We also have a job vacancy for a software engineer, which requires knowledge of both the C++ and Java programming languages. Here on the slide, we show two representations of this data as a knowledge base. The leftmost representation is a graph, where nodes correspond to entities and edges correspond to relationships between those entities. Secondly, we show this information as a set of triples, where each triple consists of an entity, a relation, and an entity. Note that in both knowledge-based representations, we only have positive triples, which represent facts, so we don't have any negative information. Now, a property of real-world knowledge bases is that they are inherently incomplete. This just means that only some of all facts are observed or available to us. So in our example knowledge base, we might not know that Ginny knows C++. Thus, we might not know whether this triple should be positive or negative. This is where the task of knowledge-based completion comes in. Knowledge-based completion is also called link prediction and takes as input the observed knowledge base that is available to us and produces a knowledge-based completion model, which can predict for any unknown triple whether that triple should be positive or negative. So it's basically just binary classification of triples. We focus on rule-based knowledge-based completion. So for example, a possible rule that could be learned might say that if a person knows Java and has 5 years of experience, then we predict that that person is bound to know C++ as well. The most common evaluation metric is the confidence or precision of a rule, which just counts the total number of positive predictions out of all predictions. Now, a knowledge base as a data format has two problems. First, as I already mentioned, they only contain positive triples and no negative triples, which can be a problem for binary classification metrics. Secondly, knowledge bases suffer from something that we call the observation bias, which just means that the observed positive triples are a biased sample of all positive triples. Or, in other words, some positive triples are more likely to be observed than others. Or, the knowledge base is not an i.i.d. sample of the ground truth of all positive facts. So take, for example, the English Wikipedia. It has been shown in previous work that a person's relationship status is more likely to be mentioned for women than for men, and for Americans than for Poles. So, the Wikipedia contains both a gender bias and a nationality bias. However, by definition, everyone has a relationship status. These two problems influence the confidence of the rule. Note that typically, we cannot calculate the rule confidence exactly, because we don't know for all possible predictions whether they are positive or negative. So the confidence has to be estimated. And these two problems make that estimation difficult. So the question that we are interested in is, how can we learn rule-based knowledge-based completion models that do not capture the observation bias? Well, current estimators of the rule confidence acknowledge the first problem of having only positive triples available, but they don't acknowledge the second problem of the observation bias. So let's first have a look at how current confidence estimators acknowledge the positive-only problem. Assume that we have, for example, a rule predicting 12 triples. Those 12 triples are shown on the lower left. These triples describe 4 different job seekers and 3 different programming languages, and the triples represent whether a job seeker knows a programming language or not. On the lower left, we show the true class labels for each of these predicted triples. However, these class labels are unavailable ground truth. We don't have this available. We only have our observed knowledge base available, which is the ground truth to which the observation bias has been applied. And in our observed knowledge base, we only have 5 positive predictions observed and 7 unlabeled predictions. So for this example, the true confidence of this rule would be 7 positive predictions out of 12. However, we only have 5 positive predictions observed. So, how can we estimate this confidence from the observed knowledge base without knowing whether the unlabeled triples are positive or negative? Well, existing confidence estimators do this by assuming that some of these unlabeled predictions or triples are negative. We'll look at the 2 most common assumptions for assuming unlabeled triples as negative. The first assumption is called the closed world assumption, which is the simplest assumption you can make. It is just assuming that all unlabeled triples are negative. So here in our example, we replace all question marks with a minus sign to indicate we assume these triples are negative. Note that by doing so, we also incorrectly assume that some positive triples are actually negative. The confidence estimator based on this assumption is called the standard confidence in literature. It will just count the observed positive predictions out of all predictions. So in this example, that would be 5 out of 12 instead of the correct 7 out of 12. The second most common assumption to generate these negative triples is a partial completeness assumption, also called the local closed world assumption, which corresponds to saying that if we know something about an entity, then we will assume that we know everything about that entity. So, in our example, note that for 3 out of 4 job seekers, we have at least 1 observed positive prediction. So for these 3 job seekers, we will assume that the unlabeled predictions are negative. For the 4th job seeker, we don't have any positive facts observed, so we will not assume anything about his unlabeled predictions. The confidence estimator based on this assumption is called the PCA confidence, and it will count the observed positive predictions out of all considered predictions under this assumption. So for this example, it would be 5 out of 9 instead of the correct 7 out of 12. So both these confidence estimators deal with a positive-only problem, but they don't deal with the observation bias. So let's quickly go back to the task that we actually want to do, which is knowledge base completion. It takes the observed knowledge base as input, and it generates a knowledge base completion model, which is just binary classification of triples. This is difficult because there are 2 problems in the data. We only have positive observed triples available, and the observed positives that are available are a biased sample of all positive triples. Now, we note that this setting is very similar to the learning from positive and unlabeled data, or PU learning setting. The PU learning setting has dealt with both of these problems. So let's have a look at PU learning to see how they deal with it. So PU learning is very much related to binary classification. In binary classification, we have examples that are labeled either as positive or negative. The goal is to learn a binary classifier. However, this binary labeled data is not available in the PU learning setting. In PU learning, we only have positive and unlabeled data, which means that none of the negative examples are labeled and only some of the positive examples are labeled. You could imagine that this PU data is generated from the unknown fully labeled data by applying a biased observation mechanism to it. In the example shown here on the slide, the positive instance space has 2 separate regions. The blue region contains positive examples that are less likely to be observed, which just means that the probability that they are observed is small. The green region contains positive examples that are highly likely to be observed, which means that these positive examples have a high probability of being observed. Now, to learn a binary classifier from this PU data, we could naively assume that all unlabeled examples are negative. This is similar to the closed world assumption. However, in this case, the learned concept is quite different from the concept that we want to learn. However, we might have some domain knowledge available about these two different positive regions. Then, what PU learning does is incorporate this domain knowledge to mitigate this bias observation mechanism to learn the correct concept. So what we propose is to view knowledge-based completion as PU learning. They both start from an unavailable ground truth containing fully labeled data to which a bias observation mechanism is applied. So the data that is available to us is a biased positive sample from all positive examples, and no negatively labeled examples are available. So let's quickly go over our contributions, and then I'll go over them in a bit more detail. First, we provide a unifying view of knowledge-based completion as PU learning using propensity scores. Then, using this view, we analyze existing confidence measures that I already mentioned before, the closed world assumption-based one and the partial completeness assumption-based one, in the face of general observation biases, and we show that they cannot handle these general observation biases. Thus, we propose two new confidence estimators using propensity scores that can handle general observation biases. We also prove that the propensity scores used in these new confidence estimators do not need to be exact, so they might be estimated from domain knowledge. And lastly, we include experiments that confirm our theory. So first off, we provide a unifying view of knowledge-based completion as PU learning. We do this by formalizing the observation mechanism using propensity scores. The propensity score is a probability that a positive triple is observed. We propose a taxonomy of different assumptions about the different observation mechanisms. So the simplest and most strict assumption that you can make is just a closed world assumption, which just assumes that all positive triples are observed. A bit more general is the scar assumption, which assumes that all positive triples have a constant probability of being observed. Next is a scarper predicate assumption, which assumes that all positive triples of a specific relation have a constant probability of being observed. Even more general is a scarper rule assumption, which says that all triples that are predicted by a rule have a constant probability of being observed. This way, the rule is a way to specify a feature for the group of predicted triples. And lastly, the SAR assumption is the most general assumption one can make. Under the SAR assumption, the probability of a positive example being observed depends on the features of the knowledge base. Now, note that the different confidence estimators might be biased under only some of these observation mechanisms. We propose two new confidence estimators as well that incorporate propensity scores to account for observation bias. So, remember, the confidence of a rule is just the number of positive predictions out of all predictions. An existing estimator is a standard confidence, which is based on the closed world assumption. Instead of counting all positive predictions, it counts all observed positive predictions. In our paper, we show that this confidence estimator is a biased estimator for the scar per rule assumption and more general assumptions. So what we propose to do is, instead of counting the observed positive predictions, we will use a weighted count of these observed positive predictions. And the way that we use is the inverse of the propensity scores. So this is the inverse propensity weighted confidence. In our paper, we prove that this is unbiased for general observation biases. Now, similarly, we propose a second confidence metric in our paper, which is an inverse propensity weighted version of the PCA confidence estimator. So now you might think, in real-world knowledge bases, these propensity scores are unknown, so you have just moved the problem. However, we prove in our paper that even when we use imperfect estimated propensity scores, the inverse propensity weighted confidence is often better than in CWA or PCA-based confidences. Thus, this means that the propensity scores might be estimated from domain knowledge. So, in our previous example about the English Wikipedia, we know that every person has a relationship status by definition, So we might be able to use this to estimate propensity scores. Finally, we analyze the existing and proposed confidence measures both theoretically and experimentally. In our experimental approach, we start from a benchmark knowledge base and assume this is the ground truth. We calculate the true confidence based on that ground truth. And then we generate different synthetic observed knowledge bases by applying different observation mechanisms to the ground truth knowledge base. And on these synthetic knowledge bases, these synthetic observed knowledge bases, we calculate the confidence estimators. So the CWA, the PCA, and our IPW confidence estimator. And then we calculate the mean square error between these confidence estimators and the true confidence. What we show here in this plot is the results for different observation mechanisms. The blue and orange indicate the existing methods, while the green indicates a proposed method. As you can see here, this also shows that our inverse propensity weighted confidence estimator reduces the observation bias, where the CWA and PCA confidence estimators do not. So, to conclude, we know knowledge-based completion is hard, because knowledge bases only contain positive triples and no negative triples, and the observed positive triples are a biased sample of all positive triples. So, our contributions in our paper are that, first, we provide a unifying view of knowledge-based completion and PU learning using propensity scores. Using this view, we analyze the existing CWA and PCA confidence estimators in the face of observation biases, and we show that they cannot handle general observation biases. Thus, we propose two new confidence estimators that can handle general observation biases using propensity scores. And we prove that these propensity scores need not be exact. They might be estimated from domain knowledge. And lastly, we provide experiments that confirm our theory. So, the takeaway message here is that by using propensity scores, as in PU learning, the observation bias can be reduced in knowledge-based completion models. Thank you for listening.